Okay guys, here we go. This is video number 4 for this section, and in this video I'm hoping to wrap everything up. We've got 2 more topics to cover, but decomposing functions, I kind of feel like it's a little faster, at least. I don't know if easier, but it's faster. And then just one application problem at the end. So first, decomposing functions, what's happening here? You're going the opposite direction of composing functions. And in general, here's how we would do it. If I have some kind of composite function, I'm going to start by looking for a function within that has all occurrences of x. So at minimum, that would mean x squared plus 2x in this case. But to me, in this particular instance, the most natural thing is the whole part underneath the square root. So I'm going to give that some name. In this, let's just call it g of x for now. If maybe a g of x is already taken, you could pick a different name, but let's call it g of x. That's going to be our inside function. Now I look back at my original function and I look, okay, anytime I had occurrence of g of x, I'm just going to rewrite that with a regular old x. So just like this, it's square root of, wherever I saw g of x, I'm just going to write a regular old x. That's going to be the outside function now. So f of x is equal to the result of what I just did, replacing that g of x with just a regular old x. So now if I compose those two things, f of g of x, I'm going to get exactly the original function I was looking for. Then you can just double check by using what we learned about composing functions in the previous video, or actually the last 2 videos. Okay, that's the general idea. We're going to jump straight to the questions now. And in numbers 11 through 14, it's kind of a little bit different though, because we don't have to pick our own f, g, and h exactly. We're already given f, g, and h to work with. So instead of doing it from start to finish, what I'm going to do is just kind of go by inspection. And then for numbers 15 through 19, then we'll do procedure I was explaining earlier. Okay, so starting with number 11, let's do that in red. We'll alternate red and blue. What's happening here? I have an inside function and outside function. Inside function looks like to me an x minus 3. So that's going to be the first thing, right? The first thing that should happen would be the g of x. And then the second thing that happens should be this square rooting, right? You see the square rooting? So whatever the result of g of x, I take a square root, which is the f of x. So notice the g of x is inside, f is outside. And as a quick check, let's just evaluate this. G of x would be x minus 3. And then I'd be taking f of that. F would take a square root of whatever is there. And so I end up with square root of x minus 3, and that matches. So that's correct. Which means f of g of x was the correct answer here. That's it. Okay, number 12. So here we have x minus 6, but this is kind of, I don't see x minus 6 here or here, right? Also, I don't see any square roots here. I don't see any double x's here. So it looks like the only thing I have to work with is a g, but it's not quite right because it's 3 and not 6, right? Well, here's a little trick, guys. X minus 6 is actually, change color here. X minus 6 is actually x minus 3, but then minus 3 again. See that? So inside function would be a g of x, and then outside function is another g of x, subtract 3 again. Okay, let's do a check. G of x takes away 3, then apply g to that. It's going to take whatever my input value was, subtract 3 again, which is x minus 6. So yeah, exactly what I was looking for. G of x was indeed the correct answer, that means. Okay, so that is correct. Okay, now number 13. Number 13, looking at what I have here, let's see, I got a square rooting going on, I've got a doubling going on, and I've got a subtracting 3 going on. And it looks like in that order. Think about the order of operations. What's happening first, second, and third? The first thing that should happen, that should be the innermost function. So square rooting would happen first in the order of operations, and then timesing by 2, and then subtracting 3. So let's write it in that order. Square rooting first, that would be f of x, right? Next would be doubling, that's h of x. So h of the result. Then next is subtracting 3, so that would be g of that result. So this should be my composite function. I said that wrong. G of h of f of x. Now let's check. So in this function, f would happen first. That's square rooting. And then I still have h to do, still have g to do. So then I take h would double it. So I'd have 2 square root of x, and I still have g to do. And then g would just subtract 3 from whatever I give it. So it'd be 2 square root of x and subtract 3. And that matches what it was supposed to be, right? So that means indeed, yes, I have the correct form here. G of h of f of x. In that, it's got to be in that order, or you're going to get something else. Okay, now last one, k of x. What's happening here? Okay, let's look at the order of operations. I have 4x right there. But how the heck do I get 4x? Well, very similar to this number 12, right? If I double x, I get 2x. But if I double that again, I get 4x. So 2 doubling should happen. That means h of x and then h of the result. That gives me 4x. Next would be the square root. So that'll be the f of that, right? Okay, so that would end up with square root of 4x. But then I got the minus 6, but we saw it before, right? How do I get minus 6 from something? Well, I just take a g 2 times. Okay, this one's going to be a little bit of a monkey to check, but let's just go through it real quick. First h gives me 2x, and everything else is still there. I got the other h, I got the f, I got 2 g's. Okay, next, apply this h. Applying the h, I get another doubling, so it's going to be 2x times 2. That's going to be 4x. So I got the f, so I got the g, so I got another g. Next, take the f. That's going to be the square root of whatever I have, which is 4x. So square root of 4x. And I still got a g, and still got another g. Okay, take that first g. It's going to be square root of 4x minus 3. Still got another g to attach. Finally, take that last g. It's going to be square root of 4x minus 3, which is square root of 4x minus 6. So, yep, matches what I wanted it to be. So there it is. Yeah, that means what I had originally was correct. Okay, so now onwards to the directions I was giving earlier, right? We want to give two functions. So we're given an f of x. We want to pick two functions, g and h. So g is going to be the inside one, h is the outside one, such that the f is equal to the composite function. And notice answers may vary. So I'm going to give you one version, but you might get different versions from me because it depends on how you pick your g of x, right? Now we have more freedom. So we could do it more than one way. But there's going to be certain obvious ways, I think. Certain obvious ways in a lot of these anyway. Okay, let's look at this first one. First one here, the most obvious thing to do first to me is just cube, right? So I'm going to say the inside function will be a cubing. And then what I'm going to do is going to take this original function, x cubed minus 2, right? And wherever I saw occurrence of my g of x, I'm going to replace that. So replace this guy with just a regular old x. So whenever I saw what I was calling h of x, g of x, I replace it with an x. Now as a quick check, let's do this. Let's do h of g of x. G does cubed, right? And then now I apply h. It's going to input whatever I gave it and subtract 2. And that's exactly what I was looking for. So that's it. That's it. The decomposition is stating these two functions so that h of g is the thing that I'm after. I'm going to alternate. Let's do some black here. Okay, now this one, obvious inside function is the x squared minus 7. Call that g of x. And then obvious outside function would just be to take the cube root of the result. Okay. Anytime I saw my occurrence, I replace that with x. Yeah. Okay, we're gonna zoom right along here, guys. Now, next one. Okay, so I look at this question. I see there's a few things that I could do. I could just do 8x by itself as one inside function, and then I have to do the other function as double square root plus a 5. But I think the easier one is just to do all this in one function and then add 5 second time. So g of x, I'm going to say is going to be 2 times the square root of 8x. And h of x is, okay, so anytime I saw occurrence of my g of x function, replace that with just a regular old x. So now if I combine those two, compose those two, I had exactly what I'm looking for. Let me give you another option for this particular question, like I was saying the first time. So I could say g of x is just 8x. So that only covers that part, right? So that means h of x would have been, just replace that 8x with the x. And then that would also work just as well, okay? But for the sake of space, I'm just going to give you one of them. So we see, as you do these, decomposing function, not so bad, right? What's happening here? There's a 4, there's a absolute value, and then there's a +5. I'll give you one option here. To me, the easiest option, do 4 absolute value of x. And then anytime I see 4 absolute value of x, replace it with just an x. So that's going to be my outer function. Just x plus 5. Easy. Easy. And you can double check these compositions on your own. If you're like in a situation where you're not sure, you want to be extra sure on a test or something, then just recompose the function and make sure it matches up. Like I did that for a few questions. Okay, number 19. What's happening here? Obvious inside function here. Again, not the only option, but to me that's the most obvious, for x plus 5. And so now anytime I see 4x plus 5, replace that with just an x. And then I get absolute value of x. Okay, I got some space here. Why don't I give you one other option? So I could have said g of x is just the 4x. And then that means I'll replace any occurrence of 4x with just an x in my outside function. So it would be absolute value of x plus 5, like that. And that'll work just as well. So yeah, not so bad. I think we're going to make it, guys. We're going to make it in this last video, one crack. Okay, last question. Last section, first. Apply composition to practical problems. So I really honestly don't have a lot to say because we already learned all the math. Now we're just applying it to an actual word problem. That's all. I was just saying like, okay, we're going to do word problem now. So a small tip though. Hardest part of application problems is often understanding what the question is asking. So just make sure you dedicate sufficient time to reading and rereading the question until you understand what's being asked. And at the very end, make sure your answer logically addressed the question. So double check, reread the question at the very end. Once you've answered, make sure that you actually answer the question. You probably heard that a lot through your schooling days, right? Your teacher is like, answer the question, make sure you read it. Okay, number 20, you work in a store where employees get 20% off of premium bug jerky. Yum. Additionally, the store is offering $15 discount on all bug jerky purchases. Letter A, find or write the function for a 20% discount. What does 20% discount mean? 20% discount means you're paying 80%, right? So f of x is simply 0.8x. That's the function for 20% discount. Oh, you know what, guys? Let's give this a better name here. We'll say t for 20. So t of x is 0.8 times x. If you don't see how that's 20%, some people like to think of it this way instead. T of x is equal to x minus 20% of x. But if you do that, you reduce it, you end up with getting 0.8x anyway, right? So that's why. I like this one better, so I'm going to stick it down. Okay, letter A done. Letter B, write a function g of x for the $15 discount. Okay, easy. We'll say that D for discount, whatever your price was, minus 15. Easy, right? Okay, letter C, use a function composition of your functions from A and B to model taking 20% off first. Okay, sure. So let's do that. 20% off first means 20% should be the inner function, right? So this is letter C. I'll do side work over here. Letter C. 20% off first means t of x is the inside function, and then I do d of x after. And let's see what is that. D of t of x. T of x is 0.8 x. D of it is get the input, 0.8 in this case, subtract 15. So 0.8x minus 15. That's letter C. Letter D, use a composition of your function to model taking $15 off first. So $15 off first would mean d of x is the inner function, and then I take 20% off. Okay, so d of x is minus 15 first. That's going to give me x minus 15. And then I'm going to apply t of x, 20% off that. So it's going to be 0.8 times whatever was the input, right? All right, in this case, that's going to give me, I got to distribute this time, right? So it's going to give me 0.8x. And then minus 80% of 15. So I'm going to punch that into my calculator because I'm not good at arithmetic. And that is $14.20. 14.2. So that's the result. Okay. So now, let's see. Letter D, that was letter E next. This is just interpretation question. Would you rather take 20% off first or the $15 discount first? So compare my two answers. Which one is going to be a smaller value? Which one is going to be cheaper? 80% minus 15 or 80% minus 14.20? I'm looking for the biggest discount, right? Bigger discount is going to be subtracting 15 because both cases I got 80% of x. But in this case, I have only 14.20 subtracted as opposed to $15 subtracted. So letter C is a better option. Letter C means taking the 20% off first. I'd rather take the 20% off first. Since it's cheaper that way. Or it would result in the cheapest cost. Yeah, so interesting, yeah, kind of interesting. It actually matters the order that you compose them in this case, the order that you take the discounts. So something to keep in mind if you're ever in a similar situation like that. All right, guys, we're done. Have a great day. See you next time.